Hello, I'm going to talk about LeetCode question binary tree in-order traversal. So for a tree, the definition of in-order traversal is to visit left subtree first, then the node itself, then right subtree. So for example, if we had 1, 2, 3, so the in-order traversal would be 2, 1, 3 because we visit this first and then record that. Then with that left subtree, and then the node itself, then that would be the next one, and then the right subtree here for 3. Okay, so the recursive solution is actually pretty standard. It does pretty much what I described. So for a given node here, if the node is not none, then we recurse the left subtree, then we process the node itself, then explore the right subtree, and we do that recursively. But I want to show what it's like for a call stack, or sorry, what it's like iteratively instead of recursively, and I'll do that with a stack. I'll do that with a stack because for recursive solutions, in essence, what it does is use a call stack, and I'll show you how it uses the call stack, and then use that same logic in the iterative solution. Okay, so we'll just take this example here. So at first, we call the function with this node here, 1, this root node 1. If root is not none, then it's not none, then we recurse root left. And when we call this recursive function here, we pop this one node into this call stack saying, hey, we're recursing, we'll visit this guy later. When we're done recursing everything, we'll visit this guy later. Great. So now we call this recursive function or recurse root.left, okay? And it turns out for this example, root.left is none. So when it's none here, we don't go through all these steps. So we go back to call stack and pop the one here. We pop it and continue do the rest of this function as normal. So we finished this guy here. We finished the recursion on the left step. So we're going to result this append this result to the value to our result array. So if we had this result array here, it would be 1, and then we recurse to the right. So pretty much similarly, we put this in the call stack here, 1, and recurse to the right. And it turns out we do have a value on the right here. So we go back up to this recursive function, and this root would be 2. This root value would be 2 that we're looking at. So similarly with 1, if root is not none, we recurse the left subtree, and it turns out we do have a value here, so we recurse to the left, we push this 2 to call stack, saying we'll visit this guy again later. First let's do recursively call in order recurse again with 3. Okay, so we're visiting 3 now, and then we're recurse root.left, so we pop 3 to the call stack. We go to the left, there's nothing. Okay, great. So we continue as normal, pop that, result at append root.val, so we append 3 as we go to the function, then order recurse root.right, so we pop this guy back here, root.right. Actually, it turns out there's nothing for right, so go back to this call for the node of value 3, pop it, and it turns out for this function we're actually done here, so we don't do anything else. Now we go back to 2. So now we pretty much did this root.left here. We do result at append root.val, okay, append 2, and then recurse to right. Oh, sorry, we go back to 2, before we recurse that right, this actually gets popped. And then we append 2 here, and then recurse.right. We put that back in the call stack. Turns out there's nothing on the right, so we go back to the to run of this recursive function and pop it. And it turns out we're done. And then we go back to 1. We already did the root. When we go back to 1, need to pop it. And it turns out after this recursive call to .write, the function ends and we're done. And then we have this result array here, and that's the solution. So we'll use this logic for the iterative solution. I guess the only difference is here when we do the like recursive root.left. Great, we push it, and then when we do the when we go to this step here, well, we do pop it and put that to the result array. When we recurse again to the right, we don't push it back again in here because we know that's already the final step. So yeah. Now I'm going to define my iterative function. Where here, side space there, for here. So what I'm going to do is initialize my stack to be empty and current node to be root right now. Okay, and so while current node is not none or len of stack does not equal to 0, so basically we want to keep iterating while our current node is of a node value, or if the stack still has elements in it. So what we want to do is, as here, as in a recursive function, just keep going left. So keep going left. So while current node does not equal none, what we're going to do is we're going to remember that node. We're going to come back to it and stack.append current node. So we're going to remember it by putting it in this stack, and then we're just going to assign current node is equal to current node dot left, just like up here. We're going to keep traversing left, but put it in the stack to remember what we have to come back to this node. Okay. So if current node is none, that means we're done traversing the left. So we're done traversing the left of here. So we're going to pop from the stack. Current node equals stack dot pop. And then append the root value to our result array. Okay, and then like up here, once we append it to our result array, we're going to look at the right subtree. Yeah, and that's basically it. That's kind of the essence of it. So what we're going to do here is comment this guy out, and then call Inorder Iterative on root. And then that should correctly populate the result here. Okay. And this is of course O of n solution because we visit each node once, where n is the number of nodes. And yes, basically once we have current node dot right, we again up here traverse the entire left subtree of that current node, like up here. Once we have the right node, we want to traverse the left subtree over and over. Okay, I'll try compiling it first. Oh, it should be current node.fail. Yep, and that seems correct. And that's pretty much it. Thanks for watching.